Welcome to the answer video of the question about glycerol production. My name is Sharon and in this video I will introduce you to the answers of the question. First, we have to start with collecting the information we got about glycerol production. Glycerol is a viscous, non-toxic transparent liquid and flows between two coaxial cylinders that are arranged vertically. Of course, to understand this whole process, a clear sketch is necessary. So the first question asks you to draw this. The purple part between the two cylinders is the glycerol. You also see that I drew the z direction upwards. So the inner cylinder is moving with velocity u against the z direction, which means that the velocity is negative. U is defined as follows. The flow can be considered as laminar and is steady state. The inner cylinder is massive and has a radius r1. The outer cylinder is hollow and has an inner radius of r2, which is 2 times r1. And the outer cylinder does not move. Furthermore, there is given that no pressure difference is applied over the length of the cylinder. In the next question, you needed to set up the differential equation for the shear stress profile if you set up a balance of the forces over a small part of the liquid between R and R plus dr with length L. To do this, we first determine this small part, which can be done easily if we use a cross-section of the two cylinders, which is sketched above. And of course, we also determine the z direction and the velocity in the sketch again. With this small part, we can think about the shear stress. Shear stress, τ, is of course this. So, setting up the force balance over the small part gives this equation. Outer surface of the cylinder times the shear stress at that specific point, so at R. And because the shear stress in the z direction in the surface with radius r has the smallest coordinate, it's positive. So in the force balance, the shear stress at point r plus dr is negative. And of course, the surface at this position is 2 times p times r plus dr. And the last term is due to the gravity force on the defined small part of the layer. So is this. Finally, it is steady state, so the sum of all forces needs to be 0. Dividing out 2 times p and taking the limit dr goes to 0, reduce the equation to this, which can be easily rewritten to the answer of the question. The next question asks you to find the velocity profile in the z direction of the liquid. Of course, there's a connection between shear stress and velocity according to Newton's law. Integrating the differential equation of the previous question gives you this equation with unknown constant 1. Combining Newton's law and the founded equation gives a new differential equation. Again, integrating the differential equation of the velocity gives you another equation and a second unknown constant. Using the boundary conditions gives you the opportunity to find the unknown constants. The first boundary condition is that it is given that the velocity of the inner cylinder is u. But because it moves against the I direction, v at all points with radius r1, so at the surface of the inner circle, is the negative version of u. And the other boundary condition is that at a radius of r2, the velocity is 0 because it is at the wall of the outer cylinder, so the fluid does not move over here. With the use of the boundary conditions, can be determined that the first constant is 0 and the second is defined as written down. Filling in this constant in the founded equation of the velocity gives the velocity profile. And this can be rewritten to an equation with only r and r2 because r2 is 2 times r1. In the last question, you needed to sketch both the velocity profile as the shear stress profile of the glycerol. First, we clearly write down both equations. With the equation for the shear stress profile, we can use constant 1 found in the previous question in the equation and rewrite the founded equation until only a definition of tau is left. We make again a sketch. As you can see, the point where the radius is 0, R1 and R2 are written down in the sketch. The boundary conditions say that at radius R1 the velocity is the negative version of u, and at R2 the velocity is 0. Furthermore, you can see that the equation for the velocity is parabolic, so the velocity profile needs to be something like this. The shear stress profile is a linear equation of which, if we fill in for the radius R1 and R2, the shear stress profile is this for radius R1 and this for radius R2. Both values are negative, so the shear stress profile is something like this. Because we have to deal with cylinders, the profiles are the same at every radius. And if we are going to think about it, it's logical that the shear stress is the highest where the velocity is the lowest and vice versa. Thank you for watching this video and good luck with the next chapter.